Okay, so we'll just get in with, so we've been talking about the first law for control volumes. And so everything we're going to talk about today starts with the full equation, sort of this messy big equation, and then simplifies from there. So we'll start with dE dt for the control volume. Oh, sorry, there's no room in here. Just kidding. Okay, so dE dt is equal to Q dot for the control volume minus W dot for the control volume plus MI dot, so that's the rate of mass flow at the inlet, times the quantity H at the inlet plus VI squared at the inlet plus GZ at the inlet. So that takes care of the energy that's flowing in at the inlet, and then subtract the energy flowing out at the exit. So ME dot times the quantity, all this same stuff for the exit. So HE plus VE squared over 2 plus GZ exit. All right, so that's the full first law for control volumes. And now we'll talk about 5 devices so first, nozzles. Oh my God, so full in here now. Nozzles and diffusers. Turbines. And compressors and pumps. And for each of these, we're just going to go through what assumptions we can make. Usually, you won't always be able to make all these assumptions, so you have to look at the problem and do the cancellations, okay? But this does give you a sense of what the point is of each of these devices. And a lot of times in the problems, this simplified form is what you'll end up using. Okay, so we'll start with nozzles and diffusers. So they're similar, they just sort of run backwards. So a nozzle looks like this. You're going from a big cross-sectional area, big surface area, cross-sectional area, to a small one. If the flow is this way. And at the inlet, you have a high pressure and a low speed. And at the exit, you have the opposite of those, a low pressure and a high speed. And we're going to make the following assumptions. First, we're going to assume that this motion is steady state. There's no material building up inside of the device. So steady state means two things to us. First, it means the time derivative of the energy in the control volume is 0. And second, it means that the mass flow rate in is the same as the mass flow rate out. So mi dot is equal to me dot is equal to m dot. We'll just call it all in. Second, we can't throw away kinetic energy because speed is an important part of what's happening here, but we're going to assume that changes in height don't really affect this usually, so we're going to ignore changes in potential energy. Third, we're going to assume that there's no heat transfer through the walls of this thing. The flow is moving pretty quickly through it, so because it's a fast flow, we're going to assume that Q dot for the control volume is 0. And then the last thing we're going to assume is, since the walls are rigid and there's no electricity or anything, it's just a rigid device, there's no work. So W dot for the control volume is 0. So let's go through the cancellations. So I'll just write it all out first. So d dt is equal to Q dot for the control volume minus W dot for the control volume plus mi dot times the quantity hi plus vi squared over 2 plus gzi, and then minus the same looking thing for the exit, so minus me dot times the quantity he plus ve squared over 2 plus gze. All right, so this goes away. There's no energy term because it's steady state. No heat transfer, no work for the control volume. There's still that like complicated work that we had to calculate, that came in and turned into the enthalpy term and stuff like that. But the walls of the control volume aren't moving, so there's no work done by the control volume. The mi dot, we're just going to call that m dot, same over here to me dot. We need to keep the enthalpy because there is going to be a change in pressure, so there is going to be a change in enthalpy. We need to keep the kinetic energy, but we're going to cancel the potential energy terms. And so what you get is VE squared over 2 minus VI squared over 2 is equal to HI minus HE. Okay, so let's think about what's going to be positive, what's going to be negative in this case. So if we have a nozzle, so the nozzle, oh, I didn't draw the other one. This is a nozzle. I got so excited to talk about nozzles. So let me draw a diffuser too. You can draw it down below if you don't have room here. But so a diffuser is just backwards. So the flow is going this way. So this time it's coming in faster and with a lower pressure. And it's leaving, whoops, I did those backwards. It's coming in faster with a lower pressure. And it's leaving with a higher pressure and a lower speed. Okay, so a nozzle speeds the fluid up. A diffuser slows the fluid down. So let's look at this equation and think about what's happening in each one of these. So for a nozzle, I mean, this is what happens in both of them. You're just exchanging enthalpy for speed in both of them. But for a nozzle, we're starting with a slower speed, ending with a higher speed, starting with a higher enthalpy and finishing with a lower enthalpy. And so if you write it just like I have it above, each of these two sides now is positive. For a diffuser, it's the reverse. So if you move everything over to the other sides, you can write this as, you could just switch the order of these. I guess let me do it that way. So VI squared over 2 minus VE squared over 2 is equal to HE minus HI. And for a diffuser, each of these is positive.
We both are positive?
Positive, yes. Okay, so let's do sort of the kind of example that problem you'll have to do with this. I'm just going to do one of these because these two things are so similar. So let's say that steam enters a nozzle at a pressure P1 of 10 bar and a temperature T1 of 400 degrees Celsius. And leaves the nozzle at, it's going to be a faster speed and a lower pressure. So P2 is 3 bar and T2 is 200 degrees Celsius. If the speed at the inlet is 20 meters per second, what's the final speed? Well, this question didn't say anything about specific assumptions to make, so we're just going to go with the form that I just came up with. There's no information on assumptions. So we'll just use VE squared over 2 minus VI squared over 2 is equal to HI minus HE. This is dealing with steam, and we have the pressure and the temperature at both cases, at both instants. So if you're dealing with water, steam, remember that we have tables available for that. So from the tables, we're going to look up H1 and H2. And you get that H1 is equal to 3263.9. Remember to always be careful with your units with these equations. You're naturally going to tend to think of kinetic energy calculations in SI units, and the units that they give you in the tables are not SI units. So this is in kilojoules per kilogram. So let's go times 10 to the third. So we're at joules per kilogram. And then the specific enthalpy at the exit, look that up for the pressure 3 bar, temperature of 200 degrees Celsius, and that's 2865.5 times 10 to the third joules per kilogram. We're given that VI is 20 meters per second. So this equation becomes V exit squared over 2 minus 20 squared over 2 is equal to 3263.9 times 10 to the third minus 2865.5 times 10 to the third. And so VE squared is 400 plus 2 times this stuff. Can someone punch that in and tell me what, and I guess take the square root and tell me what VE is?
I'm getting 892.86.
Okay, 892.9 meters per second. Okay. Any questions about that? That's pretty fast, because what's the speed of sound? Less than that, right? 350 meters per second, 700 meters per second.
Then get a sonic boom from the top.
Yeah, so don't build that thing, but that's how it works. Okay, so the next device is a turbine. And turbines, you basically use a change in pressure on the two sides of this device to produce work of some kind. It can be mechanical work, but usually it's electrical work. And it looks something like this. You have a shaft connected to, these are like side views of wheels, and the turbine blades are like this. So all this shaded part is rigid. And the fluid flows through that channel. So the fluid flows here and here. And the pressure difference, there's a higher pressure on the left and lower on the right. And that pressure difference rotates those turbine blades, and that's what creates the work. So we have a higher pressure on the left side and a lower pressure on the right side. And the assumptions we're going to use. First, we're going to assume steady state. We're going to make that assumption for all of these. And so that means the EDT for the control volume is 0. And again, it means, just like it's going to for all of these, MI dot is equal to ME dot, and we'll just call it M dot. Second, we're going to assume that there's no important change in potential energy. That seems reasonable. The third one is a little surprising because there is a change of speed of the gas as it goes through a turbine, but the contribution to kinetic energy, the contribution of kinetic energy in the first law is really small most of the time. So we're usually going to ignore kinetic energy. And actually, I think the example I'm going to do discusses that. Like, one of the parts we're going to calculate the contribution of kinetic energy and just see how small it is compared to everything else. And then the last assumption we're going to make is that there's no significant heat transfer as the gas moves through here. So Q dot for the control volume is 0. So I'll start with the full equation and we'll cancel. dEdt is equal to Q dot minus W dot plus MI dot times the quantity HI plus capital VI squared over 2 plus GZI, and then minus ME dot times the quantity HE plus VE squared over 2 plus GZE. So we assume steady state, so that goes away. We'll just be dealing with one single rate of mass flow, m. Then we're going to cancel the potential energies. And we're also going to just ignore we know it's non-zero, but we're going to ignore the change in kinetic energies. Oh, and one more, cancel the heat. And so you get the rate of work done by the control volume is equal to m dot times the quantity HI minus HE. So that difference in the enthalpies is due to the change in pressure. What about the sign of the work done in a turbine? Would you expect that to be positive or negative?
Negative.
So it is going to be, so the turbine is going to be doing work on the surroundings by sending electrical energy out into the surroundings or by rotating this shaft. And with our, sort of odd sign convention, that means that this is going to be positive. And the pressure is higher at the inlet than the outlet. And so the enthalpy is higher at the inlet than the outlet. And so both of these two sides are going to be positive. Okay, let's do an example for a turbine. So let's say that the fluid flowing is steam. And let's say that we know the mass flow rate is 1.2 kilograms per second. And at the inlet, we have a pressure P1 of 60 bar and a temperature T1 of 400 degrees Celsius. And a speed V1 of 10 meters per second. And then at the outlet, we have P2 is 0.1 bar. We don't know the temperature, but we know the speed is 30 meters per second. And it gives us a quality of 0.9. Okay, so if it's talking about quality, what do we know about the state of the water?
That it's part steam.
Yeah,
Water.
that's right. It's at the saturation temperature and pressure, and it's part water, part steam, part liquid, part steam. And so we can use the saturation tables for that, and so we don't need the temperature. So we know everything we need to know about it coming out at the exit. And what we want to calculate, so there are three parts to this. So first, let's use the standard turbine assumptions. And find the power that's generated. Second, once we've seen sort of the magnitude of the energies that we're talking about here, let's use those velocities to, see what we're ignoring in the kinetic energy. So calculate what's the error that comes from assuming the change in kinetic energy is equal to 0. You expect that to be big or small? Small, yeah. And last, let's assume that we can actually measure the power output. I mean, it's coming out as electricity, so it's not hard to measure. So let's assume 1,000 kilowatts of energy output. And use that to calculate the rate of heat loss.
Is that just the assumed inefficiency heat loss?
Yeah, that should be that's sort of the last non-zero thing that you would have to worry about. Since we'll already have calculated the change in kinetic energy, the real change in kinetic energy, we'll go back and instead of using for B and C, instead of using this simplified form here, we'll have all the terms in, we'll calculate that heat loss, yeah. Okay, so first we're going to make the assumptions of this sort of standard turbine equation. So the work done by the control volume is equal to the mass flow rate times the specific enthalpy at the input minus at the exit. We are given a mass flow rate of 1.2. Well, let's not start writing that yet. So where are we going to get these enthalpies from? We're told that it's steam. If they go through the effort of telling you a material that you have tables for, it's a good chance that you're going to use tables. We have the pressure and temperature when it's superheated vapor, and we have the pressure when it's saturated, so we know we have enough information to look this stuff up in a table. So at the inlet, at a pressure of, what did I say that was? 60 bar and 400 Celsius. The table gives that H1 is 3658.4 kilojoules per kilogram. So I'm going to write this in SI units. So times 10 to the third joules per kilogram. And then at the exit, we're going to use the saturation table. So it's saturation at a pressure of 0.1 bar. And so since some of our material is liquid and some of it is gas, we're going to have to look it up for both and then use the quality equation. So H for the liquid is 191.83 times 10 to the third joules per kilogram. And for the gas, it is 2584.7 times 10 to the third joules per kilogram. And so now we can calculate H2 as the quality times H for the gas plus 1 minus the quality for H of the liquid. So H2 is 0.9 times 2584.7 times 10 to the third plus 0.1, that's the 1 minus 0.9, times 191.83 times 10 to the third. And you get a value of 2345.4 times 10 to the third joules per kilogram. So now H1 and H2 are the two enthalpy values we can use in the first law for control volumes. So work dot for the control volume is equal to the mass flow rate, which was 1.2 kilograms per second, times the change in enthalpies. So we have 3658.4 times 10 to the third minus 2345.4 times 10 to the third. And I think that is 1575.6 times 10 to the third joules per kilogram. Per second, not per kilogram, per second. It's watts. Okay, so now let's take these two temperatures that just came out of a problem in the book, but apparently they're representative of something. That's what we're basing this whole idea on. And we're going to calculate the change in kinetic energy and just see that it's tiny compared to what we calculated so far. So the change in kinetic energy is 1/2. And this is actually a rate of kinetic energy. So you can think of it like this, a change in the kinetic energy rate. So 1/2 times 1.2 times the speed squared at the inlet minus the speed squared at the exit and you get a value of negative 480 joules.
Is that joules per second?
Yes. Does the negative sign make sense?
Yeah, it slows down things, but
That's right. So there's a really high pressure at the inlet pushing stuff through, so it's going to be speeding up as it goes through there. So the key idea here is that this is really small. Okay, so now the last one. Now we're going to throw everything, like all these other terms, back into the equation. So let me start with the equation. So dE dt for the control volume is equal to Q dot for the control volume minus W dot for the control volume plus, I'll write these M's as just, M dot because we're still in steady state, times the quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. We're still assuming steady state, so that's gone. We're still assuming that there's no important change in potential energy, so those cancel. And so now we can just fill out all the rest of the stuff. So 0 is equal to Q dot for the control volume minus work dot for the CV. Okay, so the idea here is, so remember what the question said was, so now we calculated with our assumptions, with our, some sort of major assumptions, we calculated that the turbine is generating 1575 times 10 to the third watts, right? So now we're saying, well, we actually can measure the watts coming out of it, and it's 1,000 times 10 to the third. So let's plug that in for the work and calculate what the heat loss is. Okay, so Q CV dot minus 1,000 times 10 to the third plus 1.2 times H at the inlet was 3658.4 times 10 to the third. Even though the kinetic energy didn't contribute much. We just calculated it, so we might as well throw it in. So plus 10 squared over 2, and then subtract 1.2 times the enthalpy at the exit, which was 2345.4 times 10 to the third, plus v squared over 2 at the exit, and so Q dot for the control volume is equal to positive 1,000 times 10 to the third minus 1.2 times the quantity 3658.4 times 10 to the third plus 50 plus 1.2 times the quantity 2345.4 times 10 to the third plus 450. And can someone calculate that?
Getting, I think, negative 575.12 e to the third.
575 times 10 to the third, and that's joules per second.
Hold that the same.
Okay, good. We had a thing in statics yesterday. Oh my God, it was such a mess. Like I started doing that. Like I had all the notes written out, but no like answers written down. So like, can you calculate this? And someone would calculate something and I'd write it down. And then we do the next step based on it. And then it'd be like, oh no, that first one was wrong. And then someone else would, like everyone's getting different things. I was like, oh my God.
Yeah, you got to backtrack and then figure out where you go.
Yeah, it was terrible. Okay, so does it make sense that that's negative?
Yeah, because it's heat loss.
That's right, it's heat loss. Yep. And positive Q means heat added to your system.
Yeah, I was just getting the word mixed up because I was thinking in terms of the gas or liquid doing work on the turbine, but you treat that whole system.
The whole system, yes, that's you're exactly right. Yep,
okay.
That's right. And it's the same with I guess pumps is the one that sort of confused me at first because I sort of thought like if I have a little, electric pump and I'm pumping water up there or whatever, say 10 feet high, like I was picturing the system being the pump. And so like I was sort of confused on like, yeah, but what's the height doing in there? But like the system is all the way from where you're getting the water to all the way at the end of the hose,
Yeah. So yeah, work has to be done on the system to pump the water up.
Yeah.
Okay.
Right.
As opposed to the pump doing work on the water to push the water up.
Right. Yeah, and you can actually, you use pumps also to get liquid into higher pressure areas. Okay. So pumps can do both of those two things.
It's just, by definition of your system, you want to just stay using like the same sign terminology that way you don't confuse if you're communicating with another engineer.
Yes, for sure you do. Yes. All right, so that's the end of turbines. So the last category is compressors and pumps. Compressors are for gas, and pumps are for liquid. Both of these can be used to move fluid from a lower pressure to a higher pressure. Also, a lot of times you'll do calculations with pumps where you're using that to get a liquid to a different height. So it can be used to change the height of the fluid. Okay, so I'm first going to do one that works for both the compressor and the pump, where you're going from a lower pressure to a higher pressure. So the first simplification is going to be using a compressor or a pump to move a fluid from a lower to a higher pressure. In any refrigeration system or power cycle system, you need a way to get your fluid from a lower pressure to a higher pressure at some point in the cycle. Okay, so here are the assumptions we're going to use. So first we're going to assume steady state. So that means dE dt is 0. And mi dot and me dot are the same, just m dot. Second, we're going to assume that there's no change in potential energy. So notice that one's going to be different when we talk about pumps getting fluid up to a higher, to a greater height. But for this one, we're going to make that assumption. Third, we're going to assume that there's no heat transfer. And then the last one is we're going to assume that changes in speed are negligible. So the change in kinetic energy is, we can ignore that. Okay, so the equation, if we start with d dt, is equal to q dot plus w dot plus mi dot times the quantity hi plus vi squared over 2 plus gzi minus me dot times the quantity he plus ve squared over 2 plus gze. Steady state, so we can cancel the energy, and the m dots we'll just call m dot. And we will cancel the potential energy terms and the kinetic energy terms. And then we'll ignore the heat transfer. And so we come up with a form that says W dot for the control volume is equal to M dot times the quantity HI minus HE. Physically, what is that W dot? What is that power coming in? That's just the electric power coming into the system. Okay, so is that going to be negative or positive? Right. So, I've been, for each of these, I've been writing in the form where both sides of the equation are positive. So I'm going to rewrite this as negative WCV dot is equal to M dot times the quantity HE minus HI. And now this is positive and this is positive. These are actually the exact same terms that we had with the turbine, just exchanging enthalpy for work. The difference is that with the turbine, you're getting work out, and for a compressor or a pump, you're doing work to create the change in enthalpy. So this is the same terms as for the turbine. But it goes in the opposite direction. Okay, so let me do an example with a compressor. So let's say we have a compressor at steady state. And we're going to ignore changes in kinetic energy, potential energy, at the inlet. We have a pressure of P1 of 1 atmosphere. And an enthalpy of 290 times 10 to the third joules per kilogram. And at the exit, we have an enthalpy of 1023 times 10 to the third joules per kilogram. So let's assume that the mass flow rate is 0.1 kilograms per second. And if the electrical power is 77 times 10 to the third watts, what's Q? Yeah. What's the rate of heat loss? This is mystery fluid. We're given everything we need. Okay, so for this one, since we're dealing with Q dot, we know we're not using the model exactly that I just brought up. So let's start with the original thing and cancel stuff. I know you start to get sick of writing this whole thing, but it's a good way to remember it. So d dt is equal to Q dot minus W dot plus M dot times quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. We are assuming steady state, so there's no energy. We already made the switch with the M's. We're not including potential energy terms or kinetic energy terms. So we're left with just the heat, the work, and the enthalpy. So 0 is equal to Q dot for the control volume minus W dot. And we're told that the electrical power coming in is 77 times 10 to the third. So is W dot itself, is that positive or negative? If work is coming in, it's negative. And so this is going to be minus negative 77 times 10 to the third. Plus 0.1 times enthalpy at the inlet is 290 times 10 to the third, and then minus enthalpy at the exit, which is 1023 times 10 to the third. And I think what you get here is Q dot for the control volume is negative 3,700 joules per second, or watts.
Okay, I'm good.
And then the last kind. So this is exactly, you deal with pumps the exact same way as this, it's just you'll be dealing with liquids. So one thing about pumps, you're dealing with liquids, so we're always going to be happy to make the assumption of incompressibility. Okay, with gases you can't do that. But if you're using a pump and pumping liquid from a lower pressure to a higher pressure, you can do it exactly the same way, except you can make assumptions about the liquid if you need to calculate properties. So the last thing we have to do is, what about pumps where you're raising the height of a liquid? So pumps can also raise the height of a liquid. So the assumptions there are steady state, so dE dt is 0, and the m's are all just m dot. We'll assume that there's no heat transfer. We'll assume that there's not much change in kinetic energy. And we will assume in this case that your atmospheric pressure at the inlet and the exit is the same. And so we're going to assume that there's no change in enthalpy. So the change in enthalpy is 0. Okay, so let's do these cancellations. So dE dt is q dot minus w dot plus mi dot times the quantity hi plus vi squared over 2 plus gzi minus me dot times the quantity he plus ve squared over 2 plus gze. And we'll cancel energy. M dots just become m dot. We'll cancel the enthalpies, the kinetic energies, and the heats. And so you get W dot for the control volume is m dot times the quantity gzi minus gze. And again, like the compressor, this is a case where power is coming in. And so I'm going to make these negative. So negative W dot is equal to m dot times the quantity gze minus gzi. And now both of those two sides are positive. Okay, so let's just do a real easy, quick example with this one. So say you're lifting water a height of 5 meters. At a mass flow rate of 0.5 kilograms per second. What's the power requirement? So I'm just going to use this simplified form. W dot is equal to the mass flow rate times the quantity GZ exit minus GZ inlet. So negative W dot is equal to 0.5 times, I guess I'll pull the G out too. So 0.5 times 9.81 in SI units, that's the acceleration of gravity, times 5, minus 0. And so that is, I used to know that number. What's 24.525 joules per second. So, you can write that however. So W dot is equal to negative 24.525 watts. Any questions about that? That felt like a lot. I think it's the writing that same equation over and over again.
That's the best way to ingrain it into your head, though.
Yeah, it's true. Okay, well, that's all. So, yeah, let me know if you want to meet over Zoom or anything. We have a test coming up in not too long. I think it's the 6th. So I think that's probably 2 weeks from Thursday. So, but start having that in the back of your mind. What I'm going to do next class, and I don't know, it'll take around a full class to do this, but I'm going to just go back and write an outline of everything we've done so far with the equations, just sort of let you sort of center yourselves on where we are. And after this stuff, we're going to get into the second law of thermodynamics and entropy and stuff like that. But the first exam, I'm just going to make the first exam on the stuff that we've covered up through today. So you have a lot of time to digest this stuff. Okay, talk to you later.
I had one quick question.
Yeah.
About for incompressible and ideal gas models.
Mm-hmm.
I believe it was question, I don't remember what number it was. One where you had to linearly interpolate some of the data that was coming in.
Mm-hmm.
For must have been number 5, I think, where it required a 3-step linear interpolation. Yeah. I got a different answer because I think I started with interpolating it in terms of pressure and then temperature.
Mm-hmm.
Whereas you did temperature then pressure.
Okay.
Does it make that big of a difference?
It never makes much of a difference. Does it make any difference at all? I think I said that.
I got like 3.5% difference on that.
Oh, that's a big. That's sort of a big difference, but
yeah.
Because like, if you think of a surface, and you have your 4 point.
Yeah, it was 5A.
And the real surface is doing this. How many vectors? So that's 1, 2. That should define a plane, right? Does everyone agree with me? Like in 4 points, you should be able to fit a plane.
Yeah.
That gets all 4 of those points.
Yeah, it's just.
And what you're doing.
You then put a point here, draw your line across that, and point here, and draw my line across the other direction. That makes sense?
Yeah.
For the linear interpolation, just because I did it in a different step.
Right.
Step order.
So yeah, does it not find that plane?
A plane is defined on 3 points. You'd have to.
I thought of it as a plane is also defined on 4 vectors. I mean, 2 vectors, and you have 2 vectors and then they're mirror images,
Yeah, because you have a 4-piece segment.
Yeah. And this is 2 vectors.
Yeah, effectively with my linear interpolation, like how you explained it before, where you find 2 points and then draw a line in between. Since I did the steps the other way around,
yeah.
2 points on, the other edges and drew a line in between. And
right.
That's a pretty significant difference for the answer.
Will you email me that and I'll look at it real quick? Because, it seems to me that should define a plane. Because you're right that 3 points defines a plane, but those 4 points aren't all independent of each other, you know what I mean? And so there is a plane, I think, that touches all 4 of those points. But I guess maybe the linear interpolation doesn't find it.
It's just doing an approximation of a point on that plane, right?
Yeah. I guess you're probably right.
That and then, so is it standard to normally do linear interpolation for everything? Because it makes sense for temperature, just because temperature is directly proportional to the volume. Because it's linear interpolating for these specific volumes, but pressure is inversely proportionate to volume. The ideal gas law, or I should say just in general. So should you be using an interpolation that's not like linear?
Yeah, I think you would get better results. You could get better results, but linear is always, it always gives you better than nothing, and it's easier to do by hand. So, but yes, I agree that if you knew something about the shape of the function, then you could curve fit a lot more accurately than that.
From a table, you don't necessarily have a clear cut
law
to go with.
Exactly.
Okay.
But linear always gets you in a better place than not interpolating. So.
Yeah, I see what you're saying. Okay, I'll send you what I got.
Okay. See y'all at 3:30.
Wait, what's the number again?
1324. S1324. Yeah, it's in the email. Yeah.
Okay, listen.